Hello and welcome to this real-life project on credit card fraud detection offered to you by Eduonix Learning Solutions. I am Partho Day and I'll be guiding you step by step on how to build a very effective machine learning model for detecting credit card frauds. Now, in the first step, we'll have an introduction to the problem. Now, in the second and third sessions, we'll take a look at the data set and get a closer look into the variables involved in this. In the fourth and fifth sessions, we'll be dealing with cleaning, preprocessing, and handling the imbalance in the data set that are very typical of credit card fraud data. In the sixth and seventh sessions, we'll build the real models. First, a very simple model based on a decision tree, and then we'll try to enhance the model for a more sophisticated random forest model. In the eighth and ninth sessions, I'll be verifying and comparing the results obtained in the previous sessions and summarize the whole project in the 9th chapter and conclude with the acknowledgements in the 10th chapter. Now, what are credit card transactions that are frauds? First of all, we know that credit card frauds may happen in a lot of different ways. First and the most simple is where your credit card gets lost and someone who finds it uses it for an online transaction and you are charged for that very unlawfully. The next frequent occurrence of frauds in credit cards are when you buy something in a store or go to an ATM counter and someone beside you can see the credit card number or the details on it, for example, the expiry date, and he can use it for doing transactions when he goes home, and that is the second kind of fraud. Whereas the third one is where you receive a fake phone call asking you to disclose your details. So these are the three most common ways in which credit card frauds can happen. Now, everyone, the banks or the credit card providers always tells you that never ever disclose your details to anyone. But still things happen, and we are here to build a model that will detect those frauds beforehand and can block those transactions very effectively. But there is a fourth kind of fraud that happens when bank accounts or other repositories containing credit card data are hacked by someone who is very tech savvy. So that is a very clever way of doing this, and I think there is very little scope of detecting those kind of frauds, but well, we can try and see what we can do with those data. Now, the interesting or the fortunate thing about credit card frauds is that they are very rare. About 0.1%, that means 1 in 1,000 credit card transactions are frauds. So that keeps most of us safe, but still we can't afford to have those 0.1% frauds. That's because the amount related with these transactions, these fraudulent transactions, can sometimes go to billions of dollars. So this gives us an impetus or a kind of motivation why we need to build a model that we can prevent that billion-dollar loss by building a very effective model for detecting frauds. Now, the US Federal Trade Commission even admits that it's next to impossible to completely avoid fraud. But it is possible to detect most fraud cases beforehand if we can build a very effective machine learning model, and we can have our computer learn which of those millions of transactions are frauds and which of those are legitimate. So that is what we are going to do in this real-life project. And before going into the project, let me tell you that credit card fraud transactions are the most explored domains of fraud detection. So it's a very active area of research and a very active area of learning in data science. And another aspect of credit card fraud detection is that those transactions all take place automatically. So you swipe your card and the card is debited by that amount. So that is why these models that we are going to build, they need to be very fast and very accurate and very effective. Now, the major challenges involved in the fraud detection are the huge size of the data, This comes from the millions of transactions that are processed every day, and we have lots of data to handle, and we need to find those few transactions that are fraud from those legitimate transactions. So that's a real challenge. The second challenge is that almost all, you can say 99.9% sometimes, are legitimate transactions. So those frauds are really rare, and it's very difficult to find something that is a rare thing. So you need to have a very close eye and detect those frauds very carefully, very effectively, and very accurately. Now, the third thing about these frauds are that people who do those frauds, they also are aware of what's happening around. So today you build a model and it detects most of the frauds, but the next day you see that the fraudsters are aware of your model and they camouflage themselves so that the next frauds happen in a different way. So then you have to update your model, or you have to adapt your model to those changing styles of the fraudsters. Finally, the difficulty in building a model or in trying to learn how to build a model is that the privacy of those bank transactions, they compel the banks to keep those data secret. So that means that bank won't reveal your customer information, and we as data scientists will get access to very little data. So, but still there are data, and in our next sessions we'll be learning on how to catch up those data, how to drill into them, and how to make our model depending on those data. Now, before going into the major section, we know one thing, that we need a model that has to be very simple and very fast. That's because, as I said before, the transaction happens in just seconds, and you get a fraction of a second to detect whether it's a fraud or it's legitimate. So the model has to be fast, and it has to be simple because you need to have a transparency of the model. So if you know what's happening inside, that's a feature of a simple model, then you can detect frauds more easily, and you can even improve your model. So the model should be simple and fast, and it should be also accurate. That means it should detect most of the frauds, but it should not misclassify the legitimate transactions as frauds. So there should be very few false negatives, and there should be very few false positives. So these are the major challenges in credit card fraud detection. And with that, we end up our introductory section, and a quick summary of what we learned here is that credit card frauds could happen in a different variety of ways. It could be through theft, or through hacking, or through imposters calling you over phone. The occurrences are rare, but still the amount involved is really great. So that gives us a motivation of building a very good model. The third thing is that everything happens inside the computer, and you don't have the scope for checking whether a transaction is fraud, as what happens in case of passing a check in a bank, that you can verify the signature, you can ask the person who has come to withdraw his check, but it should all happen automatically within a fraction of seconds. Now, this credit card fraud transaction is a very active research topic, but unfortunately we have access to very little data. That's because of the privacy or the confidentiality of the data involved in credit cards. Secondly, the size and balance of the data are very, unfortunately, are very huge, and the balance is very skewed, and the data are also dynamic. That is, the fraudsters always keep on changing their styles. So finally, what we learned from here is that we need a very fast, very efficient model, and if possible, we need a very transparent model that could detect fraud. So with that, we end up our introductory section, and we go to the next session very soon. Thank you for listening to this video. Have a nice day. Now, as I've said before, that there aren't a lot of data available publicly for credit card frauds. That's because the banks care for your privacy, and they don't compromise or release those data publicly. But there are ways where these data can be made available for the public without disclosing the actual information that are very sensitive, that are very confidential. One of them is available at a Kaggle website, and just you can follow this link to get hold of the data. Now, this data was made available by the machine learning group at the University of Libre de Brussels of Belgium. This is a CSV data, that is a comma separated values, which is a very universal format for all these data. They are separated by commas, and different rows denotes the different observations. Now, getting hold of the data is very simple. Just click on this link and that will lead you to the browser where you'll get this web page in front of you. And down there on the right hand side you'll see a button with a download written on it, and if you click on that it will start downloading. And remember to download it in a new folder by giving an appropriate name, and there we'll do all our analysis for this data set and for this project. Once you have downloaded the data and saved in a folder, I'll suggest you to open your favorite R integrated developing environment. The most recommended RID is the RStudio. Well, RStudio is a free software or free source software which comes at no cost. It is available for Windows, for Linux, for Mac, and you can download it from the relevant website. I'm not going into the details for that. Here you see that the data is at kccf.csv, and it is kept at the Eduonix folder under the home project's parent folder. So just make sure that this Eduonix is now your current working directory, and if you are in doubt, you can just click on the more button here with the gear symbol, and there you will see a set working directory option. Just click on that and your working directory will be set to this Eduonix folder. I hope you are familiar with the R environment, and I'll go on to read the data and to see or get a look at these features. Now, the first thing we need is to read the data from the computer to the memory, and that can be done with several functions. The most common of them is the read.csv function. So once we read the data, it comes into our environment, and we see that there are almost 285,000 observations and 31 variables. It takes almost a minute to read the data in my computer, and depending on the speed or the power of a computer, it can take a little less or a little more. Now, so these are the features of the data, and once the data is read, we can get a summary of the variables with the str function. There are other functions also called the summary function or a head function, but I prefer the str function because it's very compact. Now go to your console and type str within brackets the name of the data set. That is, I have typed str kccf, and that gives the summary of the data in a very compact manner. So you see kccf is a data frame with 284,807 observations and 31 variables. So these are the variables in order: time, then v1, v2, v3 goes on till v28. So 28 plus 1 time plus the 30th is the amount. There are 30 variables and one class variable, which is either 0 or 1. Interestingly, this class variable is 0 when the transaction is a legitimate or it's a fair transaction. The class variable is 1 when it's a fraudulent transaction. So that's the way how we know whether the transaction is fraudulent or fair, and our task for building the model is to classify all those data which are zeros from those data which are ones in the class. We'll come to that later, but before that, let us see what are the different variables here. So from time to amount, all the 30 variables are numbers. That means they are fractions given range. whereas class is the only one variable which is an integer. Now we will need to transform this integer variable into a factor variable because that will allow us to build the decision tree model very efficiently. But again, that is something for a later stage. At this stage, we note one more thing, that time and amount are the actual variables which have some meaning. Go to the Kaggle website once more and scroll down and find that these features V1 to V28 are the principal components obtained with PC, and time are the seconds elapsed between each transaction and the first transaction in the data set, whereas the amount is a transaction amount. So these two are the variables that are preserved from the original data set, whereas the other features are all encrypted or maybe anonymized in the form of V1 to V28. But principal components are something that is beyond the scope of this particular project. But let me tell you that basically principal components are nothing but linear combination of the actual variables. So that is done to preserve the confidentiality of the actual data, and with this, if we can classify our data with these V1 to V28 and time and amount, then that the same model transformed in a particular way can also classify the actual variables in exactly the same manner or exactly with the same accuracy. Now with that, we have already got an overview of the data, and in our next session we'll take a look at what are the features, how the features behave, what are the different ranges of the features, and if we can identify a few features which can be significant to our analysis. But before ending up this session, we would like to go and make a synopsis of what we have done here. We downloaded the data from Kaggle website at this link. Then we saved the data in a new folder. We opened the RStudio and set the working directory with this function. We didn't use this function, but this is an alternative that I can tell you, that set wd, the folder path in double quotes can give you the working directory to set appropriately. Now we read the data with a read CSV or any other function that you find suitable. We get a glimpse of the rows, the columns, and the features with str function. But as I said, you can also use the summary or the head function for the same, but I found str to be more compact. And we can refer to the Kaggle web page to get more information about the variables in the data involved, where we saw that there are almost 285,000 rows and 30 features plus one class, that is 31 variables in total, where time and amount are the actual variables, whereas there are other 28 variables which are the principal components of the actual variables, which are not shown here. So we work with these 30 features and try to classify the whole 285,000 observations into either of the 0 or 1 classes. So that's all for this session on the overview of the data. In the next session, we'll be dealing with how to get a closer look into the variables and try to discover a few interesting facts about some of the features in the data. Thank you for listening to this video. Meet you again in the next session. Bye. For taking a deeper look, we first try to differentiate those transactions which are legitimate from the fraud transactions. And we do this for a few features, and we start with the time feature at first. So we use this 10-line code written in R first to split the KCCF data into a true and a false splits, where the true data set are the true transactions or fair transactions where the class value is 0, and the false are the fraudulent transactions where the class value is 1. Now we use the ggplot function from the ggplot2 library to plot the KCCF true and the KCCF false data sets, or the data subsets you can say, onto the same graph by using different colors for the two splits. We use the blue color for the true one, and we use the red color for the false or the fraudulent transactions. Now I chose this color so that by using the red color we can catch the fraudsters very red-handed. this alpha equal to 0.12, that is for the opacity of the fill, so that we can see from through one of those graphs into the other one. Now once we run this 10-line code on our Studio, we get a plot of this kind where time is plotted on the x-axis, and this is the density of the transactions that happens. The blue is for the legitimate transactions, whereas the red is for the fraud transactions, as we have indicated our preferred colors here. Now let's see how we can catch those fraudsters red-handed. We come to know from the Kaggle website that the whole time interval is for about 2 months. So the data set on this Kaggle was collected for over 2 months, and in the beginning of the month and the beginning of the second month, maybe when the pay is just over, the real transactions are not so frequent. So there's a fall in the density of the real transactions at the beginning of each of those months, whereas the fraudulent transactions go over almost with equal density throughout the session, or throughout or indifferent of the time of the month. So that is one feature that we can abstract, or that we can take a look into by plotting this. Well, still we have to say that this is not so important a feature, or so deterministic a feature by which we can differentiate the frauds. We need to look at other features also, and finally our model will actually tell which feature is most important in differentiating the fraudsters from the real transactors. Now if we do the same thing for the amount, we just have to replace the time in these two lines by amount, and we get a plot of this kind. Hey, what kind of plot is that? That seems to be a very skewed plot, and most of the transactions are of very small amount, whereas the highest transactions goes till almost $30,000, but transactions more than a few $100s are really very rare, and most of the transactions happens below this $100 or $1,000. So that is why it's very skewed, and we need to take a different mechanism to get a better visualization of this kind of distribution. So the thing that I did is that I took a logarithmic scale on the x-axis. So instead of plotting 0, 10,000, 20,000, I plotted 0, 1, 10, 100 on logarithmic scale, and that gives me a very well visualized plot. Well, there are two questions here. The first question is, how did I get that plot? It needs another 2-3 lines of code, but well, let me keep this code secret from you, because there is something that you need to do for yourself and find out yourself. But let me give you a clue for that I use two functions. One is the scale x log 10 function, the other is the annotation log text function from the ggplot2 library to just scale this into a logarithmic scale. Now once I've done that, we can notice another feature, that most of the true transactions are around $1, around $2, well, around $5, around $10. There's a peak at $1 and $10, whereas it falls as it goes beyond, say, something $50. The real transactions greater than $50 are very rare and rare and rare, and more than $1,000 there are very few transactions, legitimate transactions, whereas the fraudulent transactions have a one peak at $1, the other peak at $100. Well, that is a very interesting feature about fraud transactions, that you can frame it as a very thumb rule, that if you see transactions which are very around near about $1 or near about $100, well, there's a high chance that it could be a fraud. That means maybe fraudsters try the credit card, cracking the credit card with a $1 transaction first, and then they use the credit card to withdraw some $100 or something beyond. And as you see, the credit card fraudulent transactions go till maybe $5,000 also, whereas the true transactions falls down sharply after $1,000. But still, that is a kind of hunch that we dug into the amount variable, but still it's not enough to give us a kind of very good classification of all the data set. For that we need the full model. But before that, let's go to see some other variables other than time and amount, and take a look at how these vary, the density of these vary for the fraudulent and the legitimate classes. The same thing that we did, we can just replace the time or amount by the other features V1 to V28, and I just took 6 features at random and plotted the densities for V9, V10, V14, V15, V24, V25. So these are 6 features I selected at random, but we can notice the difference between the top 3 graphs and the graphs below. The main difference that say V9 and V15 are different because here the blue and the red are overlapped, they are almost identical, whereas here V9 and the blue graph, that is the legitimate transaction, stands around 0. It is around a 0 value, it has a high peak of 0.5 density, whereas the fraudulent transactions go from maybe +3 till -10. So that means that if we know that the value of a transaction for V9 is less than -5, then we can say that there is a high chance that it can be a fraud, because the real or the legitimate transactions, the value of V9 is between say -3 and +3. It hardly goes to more than +3, it hardly goes to less than -3. So that is one way of differentiating a fraudulent transaction from a legitimate transaction, and that is equally valid for V10 and V14 as well. So here the most of the fraudulent transactions have a value of V14 less than -5, whereas almost 99% of the transactions that are legitimate are between the -5 and +5. So in that way also we can identify, or we can cut off a good portion of the fraudulent transactions with the help of this one variable V14. But interestingly, that cannot be done with the help of these variables V15, V24 or V25, because the densities or the ranges for which the densities are high are almost overlapping. See here, both the fraudulent and legitimate transactions are between -2.5 and plus say 1.25, here between -2.5 and +2.5, both of them. So it's very hard to differentiate with respect to V15, V24 or V25, but V9, V10 and V14 gives us enough ground to differentiate between the fraudulent and legitimate transactions based on these 3 values. And there are other variables also which you can try for yourself and see which of these variables are more important than the others in differentiating these 2 kinds of transactions. Well, with this we took a look of how visualization happens in a data set, and we did this first for 2 meaningful variables, time and amount. Then we did the same thing for the other variables, and to get a visualization we split the data set along the 2 classes and plot their densities so as to compare the distributions on the same graph. Now amount had a peculiar behavior, that it was very skewed and had a very small amount where most of the transactions were crowded. So we took a logarithmic transformation to distribute those small amounts into a larger space on the x-axis. Now it is possible to visualize all the other 28 variables in the same way. We tried out just another 6, but you can try out the other 22 also for yourself. And that would be a good exercise. By plotting these 6 + 2, 8 graphs, we saw that some variables are such that the fraudulent and the legitimate transactions crowd across different values for fair and fraud transactions, whereas for other variables they are almost on the same range, like we noticed for the bottom three variables, V15, V24 and V25 as far as I can remember. So these are different ways in which variables participate or variables contributes to the classification mechanism of a model. We just took a look into what happens, and this is a qualitative kind of visualization. To go into the exact model will take us another 1 or 2 steps, and maybe in the next session or the session after the next we'll be trying our hand at building the model. So thank you for listening to this session, and meet you in the next session. Bye. Now, it is said that a proper data cleaning can either make or break your project. Professional data scientists, they spend a lot of time on this step because it's very important, and all the results are very sensitive on how much and how well you do the cleaning and preprocessing. Now, if you want a more quantitative kind of view into how much time is spent on data cleaning and preprocessing, you see that on an average, data scientists spend 60% of their time in cleaning and preprocessing their data. That means it's not a child's play. It involves a lot of steps, and you need to make sure that everything is in place before you go to building the model. Now, for the basic steps in data cleaning, first of all comes removing the unrelated variables, the variables like ID or name or serial number that are actually not relevant in predicting your class. Next, you need to check for typing errors like a big O in place of 0, or maybe where the data was not available. Instead of NA, there's a normal standard in all data which R can read, a dash or something else is printed. So you need to make sure that they are all conventional and they are right. Thirdly, you need to make sure that the variable values like age, they are all relevant, and maybe it cannot be more than 100, or time interval, or a number of apples, they cannot be less than 0. With that done, we'll concentrate on the most essential part of data cleaning, that's called the missing value part. So missing values is sometimes very annoying, and we need to check how many columns or how many rows of missing values. And if a particular column has too many missing values, say more than 50%, then we need to remove those columns. Same for rows. If there are rows with many missing values, we need to remove the rows too. And these are the 2 lines of code that you can check whether our data, the credit card fraud detection data, has missing values in columns or missing values in rows. Well, this is a small exercise for you to check and make sure that missing values are not there in our data. Only keep one thing in mind, that if you come across missing values and if you want to remove the rows and columns, do not go to remove too many rows or too many columns. That will result in a loss of important information, and that can degrade the results of your modeling. So finally, if you have a few missing values in a sporadic places, then you can impute them, or you can actually have some synthetic value imposed on them with some particular packages or with the help of some algorithms. MICE is a very popular and very effective algorithm for that in R. So with these, we see that how missing values or typing errors can affect the data, and they need to be cleaned or preprocessed before we go into the model. Now, there are sometimes a few transformations that are necessary for the data. The first and the most common transformation is normalizing. Normalizing means scaling all the values between 0 and 1. That can be done with the help of this formula, where you subtract the minimum value of a variable and then divide by the range. Secondly, you can use the log transformation and take the logarithm of all values in particular columns. As we have seen in case of our variable amount, most of the values were skewed on the very lower side of the range, and when we took a log, that distributed the values almost evenly throughout the whole range. So sometimes a logarithmic transformation can do havoc and it can reveal a lot of important information. Another aspect of data cleaning is discretization. Discretization is nothing but breaking up the range of variables into a few discrete intervals, and sometimes we name them with a high, medium, low, or very high, very low, or something of that kind, so that we don't have too many values in between but just a few discrete values. Lastly, we can go for feature selection, where we don't use all the features that are given to us in the data set, but we just choose a handful of variables which we think are most important to our modeling. Now, with these, we have covered most of the part of data cleaning or pre-processing, but one thing to note here is that none of these transformations are fortunately necessary for our project. That's because of many reasons. First, one of the reasons that our model only partitions data, and that means that this model is actually invariant to scale. So whether we normalize or whether we take a log transformation, that will not affect our results by any degree. Secondly, our model is a discrete model. That means we already do a kind of discretization as well as feature selection within the model. So there is no need for an extra pre-processing step because these two steps are actually done within the model. So that gives us another edge in the data cleaning pre-processing step, that we are already done with all these. Some of them are not necessary and some of them will be done later. But in some modelings like regression or k-nearest neighbor, normalization may be very important, or sometimes feature selection can improve the model by a very good degree. So with this, we complete the data cleaning pre-processing steps that are very necessary in building a project, and we go for a quick sum up of what we have learned here. We learned that data cleaning is very essential and sensitive step for data modeling, and data scientists actually spend a lot of time doing this. We took a look at the major aspects of data cleaning, and particularly handling missing values is the most important part of this step. Thirdly, we noted that we are really fortunate that our data is clean and there are no missing values, there are no typing errors, and everything was clean. So this is inevitably the contribution of the person who actually uploaded the data on Kaggle. So he must have worked a lot of time on cleaning and pre-processing this, and we are just given the whole pre-processed data, and which is clean in every aspect. Next, we noted that there are some transformations that may be necessary. Normalization or log transformation are the most common of them, but here we don't need them because our model actually does the partitioning. Lastly, discretization and feature selection are also built in within our model, and we don't need it as a pre-processing step. So here we can end up with one simple notion that cleaning and pre-processing are either wholly done or it's not needed here, but in case of other data or other projects that you may have either on credit card fraud detection or on other kinds of classification, one or more of these steps may be very important. So that is up to you to judge which is important and which needs to be done. It's of course a matter of quite experience that will tell you which is needed in what project, and when we come to the different project, we can guide you to that particular aspect. So that's all for this session, and in the next session we'll be discussing on how to deal with class imbalance problems. So thank you for listening to this video, and meet you in the next session very soon. Bye. You see there that there are a lot of people walking, and they are of different categories. Like some of them are women, some of them have coats on them, some of them are fat, some of them are short, and so we can bother to classify either the fat people or the ladies or the people who are in t-shirts or something of that sort. Now let us concentrate on just one kind of classification. So we need to classify the persons who are in red shirts. Well, that's very simple. So have I done something wrong? Wait, just a minute. Okay, so that's a game that we need to do, and your game starts now. So your task is to identify those people in red shirts given the other features. So this is in general what a classification problem means, that the class variable that you are going to predict is actually suppressed or it's hidden from you, and you need to look at other variables to predict the class of the observations of each data when that particular class feature is hidden. So this is the typical classification problem, and it is imbalanced because only very few of them belong to one class and the majority belong to the other class. So that's why it's called imbalance, because the majority is overwhelming majority and the minority is a really rare minority. Normally in real life data sets, this kind of data is very common, where one class is very rare and most of the other data belongs to the other majority class. Now a credit card is just one of those examples, and we are here to predict credit card frauds. So we see that 0.1% of the transactions are fraud. That means it is an imbalanced classification problem, and if we need to just check up whether this figure is right, we can write two simple lines of code, like first convert the KCCF class as a factor so that it's not an integer as was read in one of our previous slides, and once you have converted this as a factor, you can just give a summary of the KCCF class, and that gives you more than 284,000 of the data is 0 and only less than 500 is 1. So that means almost 1 in 600 are frauds, or 99.83% is 0, and 0.17% is 1. So that is class imbalance problem, and this kind of heavy imbalance can actually pose serious problems in your classification. It can degrade your results unless you take care that the balancing is well done. But every project is actually different from the others, and we need to see how much this kind of imbalance will degrade our project. So we'll do that in our later sessions, but for now we'll take a look into how to balance the data with some simple techniques. The first of those techniques is called undersampling. Undersampling actually means where the majority classes are undersampled. That means you remove quite many of those majority classes and try to balance the majority number with the minority number. So one of those algorithms is called a one-sided sampling, and it was proposed in a conference in 1997. The other technique is called oversampling technique, where you actually create more minority examples through some particular algorithms. One of those algorithms is called SMOT. SMOT actually stands for Synthetic Minority Oversampling Technique, and it was proposed in the Journal of Artificial Intelligence Research a few years ago. The third technique is combining undersampling and oversampling. Sometimes combination of the two gives the best results, but of course it's a more complicated algorithm, and we need to make sure which of those give results for us. For that we need to go to the real project modeling, and we need to see for ourselves what the original data gives and what are the possibilities or what are the improvements that each of these undersampling or oversampling methods can give us. So without undermining the significance of these undersampling techniques, we will actually try out the simple modeling first, where we take the whole data without removing any majority class or adding more minority classes. We take the data as it is, and without balancing, we'll just try to find out how well we can detect the frauds. So if we have a very good classification, then we can say that balancing is actually not necessary in our case, and if we get a very bad or at least an unsatisfactory results, then we can go into one of these techniques and try to find out which of them suits us the best. So going to a summary of what we learned in this session, class imbalance is a very common in real life scenarios, and one need to handle the classes very carefully so that balance is maintained if necessary. Now our data is imbalanced because 1 in 600 transactions are fraud. Now we looked at a few ways how to balance the two classes. Oversampling and undersampling are the two main approaches, where there are many methods to do that. And of course we can combine these two. But for our project, we'll actually try out without any balancing techniques first, and if we are not satisfied with our results, we'll go into one of those techniques which gives us a better balance and a better result in terms of classification. Thank you for listening to this project. So we are done with the pre-modeling part, and in our next session we'll start the real model. So I just can't wait to meet you in the next session. So bye till then, have a nice day, and we'll have many exciting things ahead. Overview of what a decision tree is. First, decision tree is one of the simplest but very effective models for classification. The best thing about a decision tree is its interpretability or transparency. This means that a domain of credit card fraud classification opens up to very good logical interpretation through the help of a decision tree. Decision trees are built by splitting the whole data across particular values of variables. And if we go to a simple example of a decision tree on classifying people with coarse voices, we see that the first split can be done with the help of gender. So when the gender of a person is male, well, yes, he will have a coarse voice. If the gender of the person is female, she will not have a coarse voice. But if we ponder a little deeper into the problem, we'll see that even kids who are males does not have a coarse voice. So this split can be further re-split into more and more nodes with a complicated tree, but we'll be stopping at that point where the classification does not lead to better results. Now, before going to build a tree, we'll be taking a short look at the mathematics behind the decision tree. Now, there are actually two measures for deciding whether to branch a particular node, and that is given by the Gini impurity or the entropy. So these are the formula for the Gini impurity or entropy, and either of these quantities actually need to be minimized so that the splitting is efficiently done. Here Pi actually denotes the probability of finding an observation of class I within a node, and C is the number of classes. Now Gini impurity is mostly used in classification and regression trees or CART, whereas entropy is used in ID3 or C4.5. We'll be using the Gini entropy and particularly the CART algorithm for our case, and we'll use the R-part library from the R ecosystem to build our decision trees. And R-part gives a very good trees with a feasible time and acceptable accuracy. But before doing that, we'll be doing a training and test split of the data set, where we'll be using the training sets to build the model and the test set to find how good our model is. And if we want to do away with bias, we can also do a small kind of shuffling, so that if the data are arranged in a particular manner, that will be unbiased after the shuffling is done. Well, this is the code snippet for the shuffling and the training split. In line 2, the sample function is used to shuffle the data. It's shuffled only across the rows and not the columns. NTR is 80% of the rows, where 1 to NTR rows goes to the training data set, and NTR plus 1 to the whole rows goes to the test data set. And of course we don't store the class column into the test, but we do it into a different list called a test C. Test C can be recast as a data frame and renamed as class to avoid confusion later on. And once we do that, we can build our real tree by the R-part function from the R-part package, and we use the class method for the classification because our classes are discrete. So let's now go to the RStudio window and find out exactly how this code runs. Well, this is a short code to actually visualize the data, and first we can read the data here with the read.csv function. Of course it takes a little bit of time, but be patient until you see this red button here. That means it is actually reading. It's a lot of data, almost 284,000 rows and 31 columns, finding how it is imbalanced. Okay, so that gives us our KCCF with 284,807 observations of 31 variables, and now we need to convert the KCCF class variable as a factor. So once we do that, we can take a look at the summary of the class variable. So that is how it goes. As I said in one of the previous sessions, that 492 of the observations are frauds, whereas 284,315 are actually genuine transactions. So that leaves us at 0.17% as frauds. The next thing is to see whether there are any missing variables. So you can calculate the number of rows where there are at least one missing. Yeah, so there are no rows with any missing values, and if there are no rows with any missing values, there won't be any missing value in the whole data. So even if you try to print the column names with missing values, well, that will also be a null character. That means there are no columns. So we know that our data is clean. Okay. So next we can go to our building the model. So this is the decision tree model that we are going to build. First we read the data and recast this class column as a factor. We have already done that. Now we need to store the rows here as rows and as columns. So we see that here there are 31 columns and 284,807 observations is that's happened from the data frame, but we need actually these two variables here. You can set a seed as you like, and once you have done that, we'll shuffle the whole data, and a different seed will mean a different kind of shuffling, but we can shuffle the data and store it in the same place. Now the next job is to split it into a training and test set, but NTR is actually 80% of the rows. So once that is done, so that gives us 227,846. So that is 80% of the rows. So 1 to NTR rows goes to the training set, and NTR plus 1 to the total number of rows goes to the test set, excluding the class column. So we do all those things, and the class column actually goes to the test C, KCCF does test C list. So it is a list, it is not a data frame. As you can see here, it is actually a list with factor with two levels, 0 and 1, whereas KCCF.test and KCCF.train are both data frames. So we actually need to recast it as a data frame. When see here, it is one variable, that is one column with 56,961 variables, 56,961 observations. And we rename the column of the test CS class. That avoids confusion later on. So now we are ready to build our tree here, and we need to load the rpart library, and this is our code for building the tree, but we'll keep a note of how much time is required, so we'll run these three lines together. So that takes nearly 3 minutes. Well, once this tree is built, we can go to predict the observations in the test set with the help of the tree we built here. So we do the predictions. Well, that's fine, and that gives us the KCCF.predict. So if you want to view this KCCF.pred, you see that it is actually a two-column matrix. The first column gives the probability that a particular observation falls to the genuine class, and the second column gives the probability that this particular observation falls in the fraudulent class. As you can see that most of the observations are genuine, but a few, like the third one, actually is classified as a fraud by the tree, where there is a more than 89% probability that it goes to the fraudulent observations, whereas there are 99.9% probability of all the other observations that they are genuine. So when the second column value is more than 0.5, we classify this as a fraud. We do that here, and we again recast that column as a factor. So once that is done, then we can go to find the confusion matrix. For that we need a character library. Once we have loaded the character library, we can ask to print the confusion matrix. So this is basically the confusion matrix. Well, this actually says that 5, 6, 8, 4, 9 of the observations are correctly classified as the class 0, that is the genuine classes, whereas 81 of the fraudulent observations were correctly classified as the fraudulent. But there are 22 fraudulent observations that were misclassified as genuine, and only 9 genuine observations that were misclassified as fraudulent. So that gives us a sensitivity of 0.9998, that is 99.98%, but a specificity not too bad but not superb, that is 78.64%. That comes by dividing 81 by 81 plus 22, that is 103. So almost 22% of the observations are not classified as frauds. So these fraudsters actually skip our decision tree classifiers, but still we are happy that we could catch 80% of them nearly. So we get the balanced accuracy, which is the average of the sensitivity and the specificity, which is 0.8931. So if we go for a more well accepted metric, that is area under the curve, which applies better for imbalanced classification problems. So we need to load that library here and then recast the class and thread columns as ordered factors. Otherwise the AUC function doesn't perform nicely, and that gives an error. So once that is done, we can find the area under the curve here. So that is 89.31% area under the curve, or 0.8931. So 89.31% can be judged as a final accuracy of our decision tree. So once we have the numerical results, we can go into seeing how the tree is, because we noted earlier that decision trees are very much interpretable. So if you try to interpret how a decision tree, what kind of decision tree we obtained, we use the rpart.plot function from the rpart.plot library, and once that is loaded, we can view the tree with the help of just one simple function called rpart.plot. Type equal to 5 is the kind of graphic that it uses, and BURD is the blue and red that I use for the coloring the leaves. So that is how KCCF the tree is plotted. And if we can export it to a PDF, extra equal to 3 option, that gives us the misclassification rate here at the end. If you want a simple explanation of what the tree actually gives us in terms of interpretability, we can look at the leftmost branch here and try to note down what is written throughout this whole path. So that gives us this particular rule that V17 is more than or equal to minus 2.7 and V14 is greater than or equal to minus 7.8 and V14 is again greater than or equal to minus 4.7, then the class is 0. So that is what we wrote down here. But if you note here, the V14 is greater than minus 7.8 and V14 is greater than or equal to minus 4.7 can be merged into just one simple qualifier, that V14 is greater than or equal to minus 4.7. So this makes the rule even simpler, and with this we can see that we can obtain very simple rules from a decision tree, and every leaf, that is all the leaves in this decision tree, can correspond to one rule for each leaf. So this is the excellent interpretability that a decision tree offers, that we can know what's happening and what are the reasons of the fraud, and then we can even go to classify the frauds, or we can even go to catch the frauds by very simple rules. Now for the other options for plotting the tree, you can go to this particular link to get a very good documentation of the rpart.plot package. And with this we end our decision tree modeling session, but a small synopsis at the end of the session, that the decision tree is a very simple but effective model for classification. It gives very transparent models, short interpretable rules, and branching occurs on every node, one variable at a time. Gini impurity or entropy is actually used for this classification, and they are minimized at every node. Now we have built a tree with the help of the rpart package. After shuffling and splitting the data into training and test sets, we use 80% for training and 20% for the tests. And the confusion matrix and AUC were used to get the numerical results. AUC is a more dependable metric for an imbalanced class classification problem, and rpart.plot was used for visualizing the tree in a graphical form. And at the end of the session, we see that the decision tree gives us very simple rules and a great accuracy, as we saw that we had almost an 89% accuracy with the AUC metric. So that's all for this session. Thank you for listening to this. We'll have another model, a bit sophisticated model, in the next session. Bye till then. Remember last time we had built a tree which gave us almost 89% accuracy. That is a good accuracy after all, but to data scientists there is no end to better and better models. This is particularly true here because frauds involve billions of dollars loss for the banks, and even if you go for a specificity increase by just 0.1%, that can save the banks $1 million. So in addition to a good data scientist, if you can also make very good deals, then you can ask for like 1% of that $1 million, which means $10,000 for you. Well, that's not a bad amount. Also, one more thing, that if you get a little higher sensitivity, that means that fewer genuine people are harassed. Now, last time we saw that 9 genuine transactions were actually misclassified as frauds. So that's where sensitivity is 99.98%, but we can even go for higher than that to harass even fewer than those 9 people that we did. So if a better model, if we can build a better model which either increases the specificity or the sensitivity or both, then of course that's something, an achievement for us. So we'll try to do that here, and we'll be using the random forest for that. But random forests are actually different from decision trees in that there are actually many trees built. So if you build one tree, it sometimes has some limitations or some disadvantages. One of them being that it's very sensitive to noise in the data. So one particular very erratic value in your data can throw the tree to a very bad performance. Moreover, if you don't do very good pre-processing, that means a few variables can remain there, which can hamper your accuracy. And finally, if your model wasn't chosen rightly, then there can be overfitting. So overfitting is something which is a bit of complicated phenomena, but in one word, this means that it was fit too closely to the training data, but it didn't perform very good on the testing data. So it's actually a memorizing kind of model. You do the memorizing task, but when newer questions are asked, well, you can't answer them. Now, as in a forest, a bunch of trees could solve this problem. A forest means not just one tree, but many trees beside it. And if we grow a forest randomly, that means that more fruits come from very different kinds of trees. That firstly reduces the uncertainty in your prediction, and it also increases the confidence from multiple decisions. So if fruits from one tree fail due to some particular reason, maybe the weather or maybe you didn't manure it rightly, then fruits from other tree will keep your harvest to an optimal level. So that's the advantage of using many trees as in a random forest. And this random forest is actually built by taking samples of data. So each tree is built not on the whole data, but from few samples. And by using data samples, this also speeds up the process. That's because there's a small mathematics which says that the time complexity of a decision tree is actually proportional to n cube, where n is the number of observations, and of course to h square, where h is the height of the tree. So even if the number of observations are reduced, so even if we assume that the height of the tree is constant and the number of observations are reduced, then we have much less time, which is proportional to the cube of how much we reduce the number of observations. So this is actually taken from a conference paper by Martin and Hirschberg in 1996. And if we just do a small math with our case, which involves 285,000 data, and if we assume that well, it takes just 1 minute, then for a case with 30% sample, the time for running one tree will be just 1 to 2 seconds. So you can build a random forest with 10 trees, which will take just 15 seconds, which is 1/4 the time. But the interesting thing about that is that with a 30% sample and 10 trees, that means that every data is actually represented 3 times. So we use the data multiple times, and we ask different trees to actually classify our data, and sometimes that gives a very pluralistic kind of decision, and we get more confidence in that because it comes from very different sources and different outlooks on the data. If we further reduce the sample to say 25%, then the time for building one tree goes to below 1 second, and we can build 20 trees in just 18 seconds. So building 20 trees with 25 samples, 25% sample, means that every observation is used almost 5 times. So with using 3 to 5 times each observation, we can reduce the time to 1/4 or 1/3 of what we originally got in our decision tree. But however, the point is that we are not more concerned with the time, but we are more concerned with the specificity and the accuracy, because it's a one time that we build the model, and we can use the model multiple times to actually catch the frauds or certify it as a genuine. So this is where we go. We build a random forest model with the random forest package. Remember that the R is small but F is big, because it's a big forest, and with that we have to set the tuning parameters correctly. There are actually 3 tuning parameters which need to be set. First is the number of trees. Well, it can be something between 10 to 100. You can choose something in between. The sample size can be anything between 20 to 80% or even more, but less than 20% is not recommended because it will involve very few data samples. And finally, the maximum number of nodes in the tree. There is the tree that depends on the tree depth. So 30 to 70 trees means actually a 4 to 5 depth tree. Now I chose those values very randomly, just picked up some values at random. 39 trees with 49% sample size in each tree, and 44 is the maximum number of nodes in the tree. If you ask me why, I just chose it at random. There's no actually rule for that, but there's a thumb rule which gives you the range, but you can choose anything between them for your particular random forest. And let's take a look at the code. Well, most of the things is very similar to the decision tree, except that the main model is actually built with a random forest function in the random forest package. So it involves a function where class is a function of all the other variables here, which is denoted by this dot, and data comes from kccf.train that we built earlier. Well, here we set the 3 parameters, 39 trees. A sample size we set as 0.49 into NTR, where NTR is the number of training data, and max node is 44. So once we do that, our tree is built, and we can use that tree to predict the class of the test data with a very similar kind of function. We use the same random forest built here and apply it in the test data to get the predictions. Well, here the predictions are much simpler than we got in the decision tree case, and we can just store them directly as a new column in the test C data frame. So we go to our studio where we take a look at how we can run this. Well, if you already have the variables from your previous decision tree model, you can use them, or I'll suggest that it's better to do them from scratch. So this part is the same as before, where we read the data, we recast it as a factor, the class variable, store the rows and the columns in 2 different variables, and here we shuffle the data and we split them into training and test sets here. And finally, if you want to keep your data set clean, you can remove the KCCF data, because we'll no longer be using this KCCF data, but we have already split it into training and test sets. And here we again recast test C as a data frame, because it was actually a numeric variable before, and we rename this column as a class. So once we do that, we can go to build our random forest model here. So first we need a random forest library for that. Once that is loaded, save the sample as 49% of the training samples, and this is our main code here. 5-6 lines of code. Is actually one simple function which is divided into 5-6 lines for getting a better look at the variables that are involved. But I'll run this block together to get a sense of what time we actually need for building our model. So once we run this, well, that's almost the same time, marginally more. And so once we get our random forest model, we can use the random forest model on the KCCF test data to get our predictions, and we can store these predictions as a column in the test C data frame. So if you want to take a look at how the predictions look like, well, they are actually, you need to view it from here. Yeah, so previously it was a matrix with 2 columns, now it's a simple factor with just 1 column, and these are the observation numbers that were predicted. And here you see that most of them are zeros, where some rare cases you'll go through a 1, but that was a 1 here. Once we have that, then we want to get the confusion matrix, and for that we need to load the caret package. Once the caret is loaded, just get the confusion matrix here, where it says that, well, 83 of the frauds were actually rightly classified, and 56856 of the genuine transactions were rightly classified. So there were 20 misclassifications for the frauds. So these were the actual frauds where they were classified as the genuine. These 2 were actually genuine, they were misclassified as frauds. So that is where we failed in 20 plus 2 observations, and 56856 plus 83 of the cases we predicted correctly. So that gives us a 100% sensitivity, 80.58% specificity, and a balanced accuracy of 90.3%. The accuracy actually doesn't count here because it's an imbalanced data set, as we have discussed before. So we can go back to our data slides, where we can just jot these results down in a very simple form to be able to get a better view of that. So previously we got 81 of them correctly and 22 were wrong. So here we correctly classified 2 more of them, and we harassed 7 less people here. So that means the sensitivity increases by a very good amount, and specificity also increases by around 2%, because previously, if you remember, we got a 78.8% specificity, and that gives us an area under the curve which we didn't calculate there, but we can do it very simply. Use the library PROC and recast the class and spread columns as ordered factors, because otherwise the AUC function doesn't perform nicely, and when we ask for the AUC, it is 90.29%. so that means it is very sharply 1% better than our decision tree model, because there we got 0.8931. So 89% to 90% is just a 1% increase in accuracy. So we will save the banks like $10 million. Well, that's not a bad deal. Like $10 million with just one decision tree is worth it. So with that, we end our random forest model building, and we notice that we got an overall accuracy with the area under the curve metric as 90.3%, which is 1% better than the decision tree. We go to the synopsis before we end this session. So in our decision tree, we got an 89.3% accuracy, but we can go one step ahead to build a bunch of trees in what is called a random forest. Well, our random forests are better than decision trees because they give a pluralistic kind of decision from different aspects, from different overviews of the data. That reduces the sensitivity of the data to overfitting or to noises present in the data already. Finally, random forest build trees from samples of the data, so this reduces the time but also increases the confidence. So we are not more concerned with reducing time, but we are concerned more with increasing the specificity or the sensitivity, and here we see that we have done both of them. We reduced both of the sensitivity and specificities, and we use random forest package to build the trees by using the entry and sample size and max nodes as parameters, which can be tuned properly. This needs a time to tune, and it's a bit of trial and error process, and you never know when your model will perform nicely, but you can go on increasing it unless you feel that, well, it's better than what we got previously. So that's all for this session. We'll be comparing our results from the random forest model with the decision tree model, along with what other people did with their different kinds of models in the past. And with that, we'll be going to our next and final session, and I'll hope to meet you then. Thank you for watching this video. Bye. Quick summary of what we got in our previous two models. So this is a decision tree model where we got a confusion matrix that looked like this, and this is the random forest confusion matrix, and these are the respective metrics and the performance metrics. So if we again try to recall that 81 of the 103 fraudsters in the test data set were actually rightly classified, and 22 we could not classify these 22 fraudsters in case of decision trees. In case of random forest, we could classify 2 more, that is, instead of 81 we could classify 83 fraudsters. That's a real achievement. 2 of those fraudsters were caught by our random forest. Not only that, we also reduced the number of people who were unnecessarily harassed from 9 to 2. So it was a better kind of classification where instead of 9 genuine transactions misclassified, we had only 2 genuine transactions misclassified. So that is 1 out of 28,000, we can say. So here that increased our sensitivity and specificities a little bit by almost 2% in case of specificity and 0.002% in case of sensitivity. But just one note here that these sensitivity and specificities were calculated with 0 as a positive class. Now if we want to take 1 as a positive class, which is more common among data scientists, because we are actually going to classify the frauds, we are concentrating on the frauds, so sometimes 1 is considered as the positive class. Then we need to write a few more parameters into our functions, particularly where we calculate those metrics, sensitivities and specificities and all that. So this is our decision tree code, but a little altered. I just added this particular parameter in case of the confusion matrix as well as in case of the area under the curve, and we'll try to see what happens there. So I assume that everything else is already run and a tree is built, and predictions have gone to the pred column of the KCF test data frame. Now once that is done, we can run our confusion matrix with this extra parameter positive equal to 1, and let's see what happens. So there we go, and here we note that the confusion matrix is the same, 81, 9 and 22 here, and the rest goes to the 0, 0 element. But the sensitivity is now reduced to near about 80%, whereas the specificity goes to 100%. So that means our sensitivity and specificity actually swaps values. They actually exchange places. Now if we do the same for our random forest model, where we again take the positive class as 1, and we assume that our random forest is already built, and the predictions from the random forest have gone to the kccf.txt data frame. So make sure that that is already done. So once that is done, you can rerun the confusion matrix here and note what difference it makes. Here the confusion matrix is the same, but again the sensitivity goes to 80% and the specificity near about 100%. Now for the decision tree, if we want to run the area under the curve, we need to order the class and thread columns. So once we do that, we can run the area under the curve, and we see that area under the curve remains the same in case of decision trees. For the random forest, if we need to rerun the area under the curve with a positive equal to 1 parameter added, we need to first order them as ordered factors and then run the area under the curve, which comes the same. So we see that in the confusion matrix remains the same. However, the specificities and sensitivities get swapped both in case of decision trees and random forest, but the area under the curve remains the same. So that's what happens here. This is done by adding the positive equal to 1 in the confusion matrix and the AUC functions, but AUC doesn't change as we saw. Now this happens because there are some measures which actually depend on which is the positive class, but there are some measures like the area under the curve or the balanced accuracy which doesn't change even if we change 1 as a positive class or take 0 as a positive class. These are some of the measures that we didn't calculate in our previous results, but we can do here without much effort. Among them, precision and recall are very common measures, but recall is the same as sensitivity, but precision is a little bit of different. And F-score and the Matthew correlation coefficient are sometimes used by many people to actually denote how well they got their results, particularly in imbalance class problems. So Matthew class coefficient can be just abbreviated to MCC, and F1 score and MCC, they can be calculated by using the MCC functions from the ML tools package and the F1 score function from the ML metrics package. So again, if we go back to our RStudio, first we need to load that package and then calculate the precision and the recall and as well as the F1 score. So these are the values for the precision, recall and F1 score or the F score, and we need to load the ML tools package and calculate the Matthews correlation coefficient here. So that gives us 0.841 as a Matthews correlation coefficient for our decision tree. And if we want to go back to our random forest package, we need to run this to make sure that the predictions of the random forest goes inside and the thread columns, and ML metrics already loaded here. So we run the precision and the recall and the F1 score and finally the MCC. So that is 0.887. So these are the values that we get for our decision tree and the random forest package. Maybe we can use that to compare with what other people got. So here is a comparison with a paper that I found. It's a very recent paper in 2018. They had compared 12 different algorithms on this particular data set that we use, and here's the name of the paper. It's entitled Credit Card Fraud Detection Using AdaBoost and Majority Voting. It appeared in an IEEE Access journal in 2018, and there were several authors, and Randhawa was the first author, and we want to tabulate what he got there. So these are the 12 algorithms that he actually worked out, and we also add our two algorithms here. The metrics that we use are actually the specificities and sensitivities, but since it actually depends on which one we take as the positive class, like it's more universally named as the fraud accuracy and the genuine accuracy. So the accuracy of detecting frauds, it goes from 32% to 83%, where naive Bayes got the best accuracy in the frauds, and the random tree got the lowest accuracy in the frauds. And here the genuines, of course most of the genuines are correctly classified, ranging from 97% to maybe 99.9%. 988%. Random forest, interestingly, gave the best classification on the genuines, but however it gave very low classification on the frauds. So that's very unlike from what we did. So we got from our decision tree, we got 99.98% on the genuines and 78.64% on the frauds. 78.64 is a little worse than a few algorithms here, but if we calculate the MCC, that is the Matthews correlation coefficient, we see that it is quite better than the best obtained by these 12 algorithms. So the best one was 0.813 obtained by support vector machine, and the next best is the one obtained by neural network, is 0.812. So only one more above 80%, that is a multi-layer perceptron, that is also kind of neural network, but 81.3%, and we got 84.1%, that is almost 3% better than the best of these 12, and our random forest even goes another 4% better, 88.7%. So we can say that while they have used 12 algorithms and obtained an 81% accuracy, we just used 2 algorithms and got 88.7% accuracy. Of course, there's a little caveat here that these people have used a 10-fold cross validation, where we have used a holdout method where we kept 20% as test set. But anyway, the accuracies should expectedly be of the same level if you try the cross validation method. So we can conclude that our models seem to excel the dozen models that Randhawa and others have found out here. So that is a good achievement for us, and this is typically what you need to do in any project. If you are given a particular project and this project is also attempted by many other data scientists, you need to compare your results with others. But in many commercial projects, you don't have the scope to do that because you are given the data very confidentially, and you need to actually put up your best effort there, and nobody else is working on the same project. So you don't have the option of comparing your results. But if it's a more competitive or more open data set, then maybe more, other data scientists have also worked on that, and you have a scope for comparing your results. So that's what we did here. And we see that our algorithms, both the decision tree and the random forest, have performed very well. So that's where we feel more confident and we feel a little elated. We'll just end our session with just one more discussion here on the Kaggle website, from where we took the credit card detection data set, and it says that whether balancing is actually necessary. So it's a question posted by Adam Hazare. It's not a question, but it's almost a leading question. Is balancing class really a good idea? So what he did is that he took different balancing techniques, but he didn't find any significantly better performance. Rather, this performance degraded by implementing one or more balancing techniques. He did both oversampling or undersampling, downsampling or upsampling, whatever you call that. And in reply to his discussion, there were 2 other comments where Nguyen actually commented that he tried out SMODE and AdaSim, but not on this data set. It seems as it's a general comment where he has asked whether Adam has actually tried RAS boost or SMODE boost. So SMODE is a kind of algorithm which is very common among data scientists, and if you wish, you can also run that, but accuracies that we have achieved is better than what other people have done. But of course, I'm not sure whether it's the best in the world, but of course it's comparable to the best. And Gromit has just given a one-line comment that the same happens for him, that he has actually downsampled and upsampled this data set, but with no benefits. So from here we take a lesson that we also don't do the balancing. You can try a balancing technique like SMODE if you want, but I'm not very optimistic about the improvement in results there. So with that, we end our comparing session, and we know that we have performed quite better than what Randhawa has done in a 2018 paper in IEEE, where he got 12 algorithms and obtained 81.3% Matthews correlation coefficient, whereas we have got 84 and 87. So that's almost 3 to 7% better than them. So that is a real achievement in terms of data science, and we have seen that we have harassed very few people, and we were able to catch a few more frauds by taking up the random forest model in place of the decision tree model. So random forest is of course better than the decision tree, and that also comes from the logic from where random forests are built. It takes a pluralistic idea from different perspectives, different samples of the data, so it's more insensitive to noise. It has a pluralistic decision. It takes out many different perspectives. So in a nutshell, our models, particularly the random forest, is one of the best models that can be built on this credit card fraud detection project. And we will next go to our final session where we will be summarizing what we discussed all throughout our project. Okay, thank you for listening to this video. Bye. In the introduction, we took a look at the problem of credit card fraud detection, why it's important, some estimates of how much is incurred in credit card frauds, and reviewed the major challenges involved in our credit card fraud detection project, where availability of data, its size and distribution, along with the adaptive nature of fraudsters were discussed. Then we got hold of the data source at Kaggle, downloaded it, and viewed the basic features of the data set, its size, class distribution, and the variables involved. In the next session, we further explored the data along a few variables, particularly the time and amount, plus some of the principal components from V1 to V28. A few of them seemed to be important with respect to our classification problem, while some of them were not so relevant. The fourth session was dedicated to cleaning and pre-processing the data, and we observed that our data was completely cleaned with no missing values. Then there were some pre-processing steps like transformation or feature selection, which we noted were either built in or not necessary for our decision tree or random forest models built on partitioning the data. We also had a short session on what is class imbalance and how to deal with it, discussed some popular approaches, but deferred the imbalance resolution till the end of the project, when we in fact concluded that it was not necessary for our case. Next, we built our decision tree model after discussing the basics about trees and their mathematics. We split our data into 80% training and 20% test sets, built the model on the training set and tested its accuracy in the test set, where we got almost 100% accurate classification on the genuines or 0 class and almost 78% accuracy on the frauds or 1 class, which gave a splendid 89.3% area under the ROC curve. The best thing that we noted about the decision tree model was a transparency or interpretability of the rules that can be obtained by traversing from the root node of the tree to each of its leaves. Our second model was based on a multiple version of trees called random forests. Of course, it increased the accuracy calculated through area under the curve by 1%, harassed fewer genuine customers, but what's more, RF models give better confidence and are less sensitive to noisy data. But as the theorem in mathematical philosophy says that no lunch is free, we lose the simplicity or straightforwardness of rules that we got from our earlier model. Finally, we compared the results that we obtained from both our models with what other people have done and found that the decision tree and the random forest gave superior classification than 12 other models reported in a recent IEEE paper. At the end of our project, we may conclude that both our models fared pretty well with globally competitive results, and we also found that other people on Kaggle did not find balancing to have improved their results, at least in case of this particular data set. So that's a summary of the whole project in a nutshell. We will end our project with a short acknowledgement section. First, I would like to thank Professor Shubhabrata Datta of SRM University, who in fact brought me to the field of machine learning and gave me one topic after another to work with on his huge material science data repository. Then my sincere thanks to Professor Ashok Banerjee, who inspired and guided me to teach online courses. He also teaches great courses for the Liverpool University Online. My next vote of thanks goes to my employer, Sri Jagannath Banerjee, who gave me the first chance to teach machine learning and data science courses for some faculties of my institute. And of course, Eduonix Learning Solutions owe a keynote of gratitude for inviting me to deliver this project to you and hosting this on their platform. The Machine Learning Group of Université Libre de Brussels did a wonderful job for the Machine Learning Society by donating this marvelous piece of clean and preprocessed data on the Kaggle website. And of course, without your appreciation, everything reduces to just nothing. So I hope that you would enjoy this project and find the contents of this course very helpful to advance your machine learning skills and data science knowledge through real application by working out the codes yourself. My best regards for you. Now, here are a few picture credits. So this is from Pixels. This and this are from Pixabay. And this picture is taken from all free downloads. And finally, a few software credits. Of course, R project, the R Studio for doing the codes and running them, and a LaTeX, the environment in which I prepared the slides. They all owe a word of thanks for this project. So I end the project with a small legal disclaimer. It says that while I have tried to do my best in working with all the codes and preparing every information which should be correct to the best of my knowledge, but still no one can be perfect. So I refrain from assuming any responsibility and blah blah blah. Okay, so I hope that you have enjoyed this project and you'll like its contents, and maybe we'll be meeting further in more projects to come. Thank you and have a nice day. Bye.